Good day, this is Module 8, Genetic Algorithm. Recall the definition of artificial intelligence is simulation of biological intelligence on a machine such that it becomes efficient enough to identify and apply the right information to solve a problem. And some algorithms, techniques, or tools of artificial intelligence would be artificial neural network, fuzzy logic, genetic algorithm, particle swarm optimization, and so on. If you remember, artificial neural network, it simulates or tries to simulate the human brain or the human nervous system. Some of the features of artificial neural network is learning or finding useful information from data. So artificial neural network be able to model the relationship of inputs and output of data. And a typical some examples of the application of artificial neural network would be to predict weather given historical data, image classification, and so on. Fuzzy logic, it's simulation, or it tries to imitate the way human beings make decisions. So it produces outputs given several inputs. And we have looked at an important application area of fuzzy logic, that is the fuzzy logic controller. Genetic algorithm is inspired by biological reproduction system, and it is used in optimization problems, in finding solutions to optimization problems. Similarly, particle swarm optimization is an AI algorithm to find solutions or optimal solutions to an optimization problem, and it is inspired by swarm behaviors of animals and insects. What are optimization problems? An optimization problem seeks the best value of a variable such that a quantity is maximized or minimized. The quantity to be maximized or minimized is called a cost function, C. So imagine you have a function, you call it C, and it is a function of x. Then the optimization problem becomes find x such that f is minimum, and that minimum value of f of x is called C optimal. An example of optimization problem is to determine the size of the 240 milliliter can such that the resultant cost is the cheapest. So cost here refers to the price to produce a can. Assuming this is the can, it has height and d, and the volume can be given by this equation. The area is given by this equation, and we can assume that perhaps the cost to produce a can is given by, or it is related to the area. So our optimization problem reduces to this: find the diameter and height of a can such that the area is minimized, because we assume that the cost is proportional to the area. So genetic algorithm can be used to solve optimization problems as this. So we can use the algorithm to find the best values of D and H such that A is minimized, or the cost. So it is, like I said, it is inspired by biological reproduction system. Perhaps you have known already that we consist of cells, and in every cell we have chromosome and DNA and gene in each DNA strand that determines who and how we are. So when reproduction happens, information from the parents are swapped and switched around to produce offsprings. So the exact process is complicated and is beyond our scope. But for now, I just want to say that in reproduction, to produce new offsprings, there are few processes that happen, and in those processes, informations are swapped and delivered from one parent, from parents to the offspring to produce the next generation. So inspired by that, scientists have developed a genetic algorithm specifically to be used in optimization problems. So this is the flow, a typical flow of the genetic algorithm. First, we generate a generation, we call it generation 0 randomly. So you can imagine there are a number of individuals representing solutions to a problem, and they are generated randomly. We evaluate the fitness or the fitness values of each individual. Here, fitness is a common term used in genetic algorithm to denote the cost value. Remember, in optimization problem, we want to minimize a cost function. So fitness here refers to the value of the cost function. So is the optimization criteria met? Have we found the smallest or the biggest value? If yes, then we extract the best individual and we translate it. If no, we have to do these three processes over and over again: selection, crossover, mutation. Once we have done this, we have to evaluate, and this process repeats, or this process repeats until we have found the best individual. Let's see in detail how this can be done. So assume that the blue line is our cost function, and like I said, the value of the cost function or the cost value is normally denoted as fitness. So if we have decided that in each generation the number of individuals that we have is 5, so at generation 0, these are the individuals 1, 2, 3, 4, 5, and the fitness value is given as such: 1.88 minus 0.19 and so on. So 1.88 refers to the cost value as produced by individual 1, right? Individual 2 is here and the cost value is minus 0.19 and so on. So the individuals represent the possible solutions to our optimization problem, and the fitness values are the cost values. Remember, we want to find a solution that gives us the smallest or the biggest cost value. So in this particular example, we are interested in minimizing this cost function. So we want to use genetic algorithm to give us this point here, because we know by observation that this cost value is the smallest. So each individual in a population has to be converted from decimal values to binary strings to perform the crossover and mutation operations. So remember, we have selection, crossover, and mutation processes to be done in every generation or iteration. So this 5 individuals is called a population. So we know that individual 1 is just a term to represent 1.37. This is 1.37. And individual 2 is a term to represent the number 2.41. Individual 2 is 2.41 and so on. So we have to convert this to binary value. So for example, 1.37 becomes 0011, 5.33 becomes 1100. So we'll be carrying out the selection, crossover, and mutation processes on this binary representation of the individuals. And at this point or at this level, you know how to convert decimal to binary and binary to decimals. I will just skip this slide. So the first step is to do selection. What we do in selection is to generate a list of individuals so that we can select them according how fit they are. So one of the approaches in selection process is called the roulette wheel selection. What we do is that we have to make sure the chances of picking up a fit individual is higher than chances of picking up a less fit individual. In other words, individuals that are fit, for example, individual 4 is very fit. Remember, we are solving a minimization problem. Individual 4 is very fit, so it has to appear in our list the most number of times. So we have individual 4 appearing or repeating itself 1, 2, 3, 4, 5. And from here we can see individual 1 is the least fit individual. So it has to appear the least number of times. And here it appears only once. And the rest of the individuals appear here accordingly or according to the fitness level. The more fit it is, it appears more frequently, and the less fit it is, it appears less frequently. So now if I ask you to close your eyes and select one individual, the probability or the chances of you selecting a fit individual is higher than the probability of selecting a less fit individual. So this is crossover operation. So what we do in crossover operation is that we have to select, first we have to decide how many individuals that we want to produce out of the crossover operation. I think perhaps it'll be better if I just skip forward and let you know what do we do in the new generation. Remember, this is an iterative process, so we have to do the selection, crossover, and mutation over many iterations. So each iteration in genetic algorithm notation we call generation. So in generation 0 we generate random population, random individuals. In generation 1 we have to generate new set of populations, and this is carried out by carrying out the selection, crossover, and mutation processes. So there are a number of parameters that we have to decide. One of the parameters is elite. So if I say elite is 1, that means the fittest individual from my previous generation will be carried forward in our new generation directly. So in this example, elite equals to 1. So this individual is the fittest individual from the previous generation, so it's brought here directly. Crossover fraction is a number between 0 and 1. Basically, this represents a proportion of individuals in the new generation that are produced by the crossover operation. So in this example, 3 individuals have to be produced by the crossover generation, and the remaining individuals have to be produced by the mutation operation. So you know what is elite. Let's see what is crossover. I'm going back. So in crossover operation, first we have to generate the roulette wheel list. Next, select 2 parents to produce this number of children, which is output of the crossover operation. But you cannot just select any 2 from the roulette wheel list. We have to give another parameter, which is PC. So if PC is 0.5, that means you select two parents only from the top 50% of the list, which means 50% of the fittest individual, top fittest individual. So I select two parents, and this is, let's say this is parent 1 and this is parent 2, and here we are assuming we have 9-bit representation or 9-bit binary number to represent each individual. So how do we produce a child? From here we can start from the left or from the right, doesn't matter. If we start from the left, we choose randomly either this digit or this digit. So if the algorithm or the random function gives us the first digit, so 1 comes here, and we go to the second position, again we choose randomly either 1 or 0, either top or bottom. If you choose bottom, then 0 comes here, and we repeat for the rest of the positions. And this is just one child in our new generation. Remember, we have to repeat this process, select another two parents, and do the crossover process to generate new child for this many children. So it's just a random selection or randomly choosing the two positions, one of the two positions, to determine either 1 or 0 of each bit in our binary number. How about mutation? Again, in mutation we choose one parent from our roulette wheel, but it has to be determined by PC, the number PC. If the number PC is 0.3, that means you choose one parent from top 30% fittest individual. So choose one. This is your parent. We have to choose a random position or random bit and toggle that bit. So if your random generator says this is the chosen position or bit, you toggle from 0 to 1, and this becomes your new child in your new generation. So that's it. You will get a new generation. And again, you compute the fitness, and you can see, for example, if originally we had 5 individuals in generation 0 generated randomly, the black points. In generation 1 you have the red and green. So green represents the best individual or the fittest individual in current generation, and red represents the new generation. So because the points are overlapping, you only see 3 points, 1 2 3. By right you should have 5, because in each generation the number of population, the population size is 5. It remains the same. It doesn't have to be 5, but in this example is 5. You can set it to be 50, 100. It depends how complicated the problem is. In this particular problem, the number of this population size is 5. So you should see 5 total red and green points here, but because it's overlapping, you only see 3. So this is the feature of genetic algorithm, where as we progress through the generations, all the individuals will converge to the optimal point. So in summary, this is how the algorithm works. In generation 0, you generate randomly a number of individuals. You have to decide what is n. Then you have to do the crossover selection, crossover, and mutation over and over again to generate new generation. So first you generate the roulette wheel. So all of a sudden from 5 you have 15 now. This is to increase the chances of selecting fit individuals to be carried forward in the next generation. So from here you choose do, you do the crossover. How many crossover child? It depends on this parameter. How many elite child? It depends on this parameter. Remember, elite, if you choose elite to be 1, that means whatever fittest here, you just carry forward. This is a mistake. This should be minus 1.46. Let me just quickly change it. Individual 1, yes. Right. In mutation, again, you choose one individual. You have to randomly choose a bit and toggle it. And how many mutated child? It depends on these numbers, right? Because if you choose elite to be 1 and this is 3, then 1 is the mutated child. So you have to repeat this process over and over again until you find the best individual. All right, let's look at an example, right? This optimization problem concerns with minimization or maximization of mathematical equation. So you have this mathematical equation. Obviously, you want to find the value of theta such that C is smallest or minimum. Even though this seems to be trivial, but this represents a cost function to be minimized in practical optimization problems. And if you plot it, this is how it looks. And obviously, you don't have to use genetic algorithm to find this point, because from observation, you can just see it, that this solution here will give you the smallest cost value. But in practical problems, due to multidimensional nature of the equations and the problems, you won't be able to visualize as easy as this. But this is just the demonstration of the feasibility of the genetic algorithm. So objective, find the value of theta such that the mathematical equation is minimized or maximized, but we are interested in minimization. So this is the solution, this point here. So we want to use genetic algorithm to find this point here. And you know that I don't have to repeat this, because you know that every individual in a population in every generation has to be represented with binary strings. You have to determine how many bits you want to have. This is a MATLAB code that I will show you shortly. Let's jump to the simulation. Perhaps it'll be clearer there. So this is the MATLAB code. So let's try to run it. So as you can see, all the points converge quickly to the optimal solution. So green is the best solution in every generation. Black is the individuals in generation 0. Red is the individuals in current generation. Okay, let's run this again. As you can see, it does find the best solution rather quickly. So once again, if you're wondering how come I have very few points, few red points, because my population size is 30. I should have 30 red points at each time. It's because some points are overlapping. All right, so every generation we have to generate 30 individuals, and as I said, the algorithm, the genetic algorithm, is designed such that in every generation the individuals converge closer and closer to the optimal solution. So that's why you can see, yeah, it looks like few red points, fewer than 30, but actually there are 30 red points. Okay, that's about it. Let's go to the next application or next example. Biggest square in a circle. So this optimization problem concerns with determining the biggest square that can fit in a circle. So imagine you have a circle of diameter 2. The diameter is 2. You want to find the biggest circle. The term biggest here refers to the area, obviously. So the objective is find the coordinates of the corners of the biggest square that can fit in the circle. So obviously you can have many square, right? You can have a circle square like this, you can have a square like this, but which square is the biggest that you can find that fit nicely inside the circle? So again, this is trivial. Maybe you cannot think of a practical application for this example, but this is interesting. And it's more interesting that this can actually be solved by using genetic algorithm. So let's look at the simulation. So let's guess. Because this problem is easy, you can easily guess the solution, right? So obviously the biggest square should have the diagonal to be 2, right? Because if the biggest square should have diagonal equals to 2, so we can compute the sides. So if the diagonal is 2, that means by using the Pythagoras theorem, if I say this is x and this has to be x as well, x squared plus x squared equals to 4. And we can guess what should be x, right? So let's go to this simulation. So this black square is the best square in generation 0, and the red squares are the best squares we got in every generation, and green is the best that we have got. So if we check the results, the area that we got is 2, which is expected, and therefore this is the coordinate of one of the corners of our square. So this is the green one is the correct answer. It is indeed the biggest square that can fit in our circle. So genetic algorithm has managed to find or give us the right answer. Let's look at another problem, can problem. The cheapest can, like I've briefly explained earlier. So here we want to find the size of a can with the cheapest cost. Objective, find the diameter D that result in the smallest area A, because we assume the cost is proportional to the area. But the can has to have a volume of 240 ml. So if you don't have this condition, the algorithm will give you 0, 0, D0, H0, and A equals to 0. Yeah, but that does not really solve the problem. So that's why this kind of optimization problem is called constrained optimization problem. That means you have to find D and H such that the volume is 240 ml and A is minimum. So you can encode these specifications in the genetic algorithm. So let's see simulation. So you will see the can to be changing over generations. does it? Perhaps you cannot see it that clearly. Let's run this again. So it was changing if you saw it. So the changes are very small, so that's why you don't see the changes in the can size. So anyway, this is the can, the best can that we can have, or the cheapest can we can have in generation 0, and this is the best can that we, or the cheapest can we have or we produced. This is a curve of, because we have the equation and it's a simple equation, you can plot area versus diameter, and obviously in this point the green lines, there should be green behind this red as well. The green lines represent the best answer, or the best diameter that produces the cheapest can diameter and height. And the red line is given by our genetic algorithm. So it does give us the value of diameter and height. And this is the value, diameter and height, for the cheapest can. All right, let's look at another example. This is the traveling salesman problem. This is a classical optimization problem where a salesman needs to travel to a number of places. The salesman can only visit each place one time only. In our example, the salesman is to start his journey from Menara UMW, this is an actual office in KL, to the following places, but of course not in particular order. So from UMW, the salesman has to go to UTM, Smara, KLCC and Sunway Pyramid. So he can only visit these places once, but he has to cover all the places. So which sequence the salesman has to use such that the total journey is shortest? So these are the distances between each place. So from UMW to UTM is 6 kilometer, UMW to KLCC is 1.1, and so on. So all the distances are given here. Objective: find the shortest distance that the salesman can possibly travel. So we can do this using genetic algorithm. So if the salesman travels from UMW to Sunway to KLCC to UTM, this is how it looks like, and we can add on the total distance and see. This is another route, UMW, Sunway, UTM, KLCC. Obviously this is very long. UMW, KLCC, UTM, Sunway, UMW, UTM, KLCC, Sunway. So in this optimization problem, the salesman's travel distance is to be minimized. First, present the distances in a table. So you can put these distances in a table. So this is how it looks like. In our code, I actually have this matrix called dist, and each individual in a population can be represented as a binary string. So now our individual consists of destination, right? In our previous optimization problems, for example, if we looked at the can problem, our binary strings or individuals represent the diameter and height, and when we looked at the square in a circle problem, the individuals probably represent the coordinates and so on. So here the individuals represent 3 destinations. So this is destination 1, destination 2, destination 3. So this particular string really encodes UMW, KLCC, UTM, Sunway. KLCC, why KLCC? Because KLCC is 3 and this is number 3. UTM number 2, this is 2. Sunway number 4 and this is 4. So the fitness or the cost function is simply the summation of the 3 distances. So this is what we want to minimize. All right, let's look at the simulation. Here I cannot have any graphics for you. I just have the final answer. So it says the sequence is 3 to 4. What is 3 to 4? 3 to 4 means from UMW to KLCC to UTM to Sunway Pyramid. KLCC, UTM. So this one. So genetic algorithm tells us that this is our shortest distance that the salesman can possibly travel, and the distance is given by 27.4 kilometers. So there we go, everyone. This is genetic algorithm. I hope you have learned something here, and thanks for watching.